Hitachi, as some of you might know, is a giant industrial conglomerate, and it's in several verticals from energy, urban development, transportation, healthcare, finance, so on and so forth. And over the last several years, what Hitachi has been trying to do is build new solutions based on AI, blockchain, and so on and so forth for some of these industrial verticals. So a lot of my experience at the Industrial AI Lab is not necessarily in the consumer space, but much more in the industrial space, and I'll talk to you from that perspective. Specifically, Hitachi has a research center in Santa Clara, and that's where I'm from. And what we're doing right now is working with a bunch of customers, both internal to Hitachi and external customers, and trying to see how machine learning, AI can influence and bring new solutions to forth for these customers. So over the last several years, we have worked in a bunch of verticals from mining, automotive, oil and gas, fleets, blah, blah, blah. And I'll try to give you some flavor of those use cases. So this was on personal sensing. I work much more with machines, but I sort of pulled out some examples of where we have used sort of personal sensing in industrial use cases. So one is very similar to what Yuri was saying around automotive, right? So most of our cars or vehicles are instrumented quite a lot. But this particular one comes from fleets. So as you know, people who do long haul trucking, the drivers often get tired. So what Hitachi is doing is coming up with systems wherein you can monitor the driver for facial expressions and also look at the heartbeat and see if the driver is really fatigued or tired. And if you find out the driver is fatigued or tired, then you can warn the driver, alert the driver, and then take precautionary measures. So this is sort of an important application from health and safety perspective. The next one is around insurance. So this is very much trying to profile drivers to see if they are risky or not. This is much more in the consumer space. And it turns out that even just with the GPS data, you can disambiguate any two drivers with close to 90% accuracy without using any of the deep learning that Yuri did. But apparently most of us have a pretty unique driving signature in terms of how we turn, how we accelerate, how we deaccelerate, how do we respond to a stop sign, and so on and so forth. And so first thing you do is you're able to first characterize a driver based on their signature. And then if you have their driving data in terms of heart braking, then you can characterize how risky they are or not. So one of the challenges here when you work with a pretty large insurance company was the number of actual accidents are very, very low. So most people don't get into accidents, right? So if you're trying to assign a score simply based on accidents, it turns out to be misleading. So we had to look at things like heart braking and acceleration and so on and so forth. And therein lies a lesson wherein that if you don't have high quality label data, and if you try to make inferences based on lack of label data, then it can often be misleading. And that is one thing that you need to think about carefully, especially around personal sensing or autonomy. The other use cases on manufacturing. So in manufacturing, there are, even today, there are a lot of operators. They do a bunch of things. And not every operator is of equal skill level, right? Just like in every walk of life, there are operators who are very good, and there are operators who are not really that good. So it turns out that you can, just like you can create a signature for a driver based on the GPS data, you can also create a signature for operators in other domains. So driver is nothing, for me, is nothing but an operator of an automobile, right? Similarly, an operator in industrial setting is operating some equipment. And the way you can create a signature for a driver, you can also create a signature for an operator. And then once you have a particular signature for a driver, you can correlate it with their performance, with their safety, and with their track record. And once you have done that, you can begin to compare operators who are very, very good and operators not really good, and then begin to make recommendations on how operators who are maybe new to the job or are not as good as some of the most skilled operators can improve their performance. So this turns out to be actually a very useful use case in the manufacturing domain, where even now a lot of things require very precision sort of tasks that humans do. And therein, if you can improve operator performance, it actually has significant impact on manufacturing bottom lines. Then in healthcare, we're working on something called rapid response system. So when you get admitted to a hospital, hospitals very often need to decide whether you need will you need to go to emergency care or not, or ICU rather. And today, most of these systems are based on rules. So you have some rules saying if this and this is there, then you might need to go to ICU. It turns out that if you are collecting the data about them, including the medical history and real-time sensing data from where they are, you can do much better than these rule-based systems. So the accuracy improvement is approximately 60% from the baseline. I can't give you numbers because this is still not published results. But from where the current standard is with rule making, sort of manual rules, if you build sort of a deep network on the data that you're collecting, then you have a much higher accuracy in terms of predicting whether someone will need to go to ICU or not. And it can make a difference between life and death. So if you know someone needs to go to ICU or not, then you can take proper preventive measures and really have a significant sort of impact on the outcome. And finally, in societal sort of case, this is especially true in Japan, there is a significant portion of population that is elderly and is getting older. And the proportion of the population that is elderly is actually increasing. And very often you can't find human caretakers to take care of your elderly population. So in this case, this particular case, I believe personal sensing can really be very important. So you can keep track of an elderly patient. You can make sure that whether they're taking their medicine on time or not, or whether if they've fallen or not, if you have. So you should sort of build these houses which are sort of completely wired up. And you can keep track of people whether they are okay or not. So this sort of intervention in terms of being able to monitor the elderly, I think is very significant, something we should think about in terms of improving outcomes. So these are some of the use cases that we have worked on in the last several years. This is not just a US team, but also we have a pretty big AI lab in Japan. So we work quite collaboratively with them to sort of work on some of these solutions. So in some final thoughts, because I thought this was a panel, I should say something more interesting than simply use cases. In my experience, especially working with the industrial use cases, operationalization of your AI is non-trivial, right? So if you think about it, if you're recommending something to someone, I'm recommending to you whether to buy a laptop or maybe a 13-inch laptop, 11-inch laptop, that's not life-threatening. But in industrial scenarios, if I make a wrong recommendation, somebody can lose their life, right? So operationalizing your AI is extremely important. That's something that as a society, as AI practitioners, we don't think about enough. So whenever you think of operationalizing your model, please think about what are the constraints, what is the true cost of a false positive, false negative. And ultimately what you're trying to operationalize is optimization problem. So unless you're able to superimpose an optimization problem on top of your machine learning output, you need to be really careful, right? So because you really need to take into account true costs of failure. So to give you an example, one of the problems in industrial settings is failure prediction, right? So people want to predict failures all the time, and and the algorithms are never 100% accurate. There is a trade-off between false positive, false negatives. Now, if I'm doing failure prediction for an aircraft, if I have a 1% probability of failure, then maybe I should ground the aircraft. But if I'm doing it for my own car, it doesn't really matter, right? I can go with 90% failure probability, right? So because in the case of a flying, the cost of failure is really, really very high. The second thing I have learned is that in general, people don't like to be monitored, right? So especially if you're working in manufacturing, if you go to a union shop, it is very difficult to instrument, right? The union workers don't want to be monitored. And this is, I think, basic human nature. We don't like to be told what to do. We don't like to be monitored in terms of of what we are doing. And remember the first use case I talked about was from fleets and truckers. So one sort of tidbit is if your data science career doesn't take off, become a trucker because that is the hottest job right now. Seriously. So you cannot get enough truckers in the field. And so now when you're trying to sort of monitor the truckers, they really don't like it. So for the companies who want to increase their safety record, it's sort of trade-off, right? So on one hand, they really want to improve the safety, but on the other hand, these truckers were really very sort of difficult to find, even more harder than data scientists these days. is how do you solve this problem? And then my last point, because I work in industrial AI, is easier to work with machines. They don't have feelings. And there's no sense of personalization or privacy. So please work with machine data. There are a lot of interesting problems in industrial AI that need to be solved. Thank you.